Greetings everyone, we're going to be talking about forces and free body diagrams. Here we have a free body diagram on this cup. We have a force exerted by me, my F hand on the cup. This is our convention. We do what is doing the force on the object. And then we have friction, which is moving to the right. And the way that we figure out which direction friction is we need to know which direction does the object want to move. If I'm not pushing on the cup, there's no friction force here, there's no acceleration, the cup is just sitting here. And in that case, we just have gravitational force pulling down and normal force of the table exerting back up onto the cup. If I am pushing on the cup, then this is going to make the cup want to move to the left if there were no friction, and so then we're going to know that our acceleration should be to the left, and friction opposes the direction of motion, so it's going to be pointing to the right. We're going to be looking at free body diagrams like this and many other different scenarios in this lecture today. First, let's look at what kinds of forces that we can have. We have two different broad categories. We have contact forces and long-range forces. These contact forces we're all very familiar with, though we might not be familiar with what this name of the normal force is. So let's go by each of these individually. So friction force, we just talked about this with the cup and the table. The important thing about friction is that it's always going to oppose motion. So this opposes motion. So you're always going to be fighting friction. Drag does the same thing. Drag is the air resistance that object feels. So these are going to act very similar. And how we're going to draw them for free body diagrams. We also have tension. So tension is an important role whenever you have maybe an object hanging like this. You want to hang a mass here. Maybe a picture from the wall or something like that, from a string. So then what keeps the picture from falling down? Because the picture frame always wants to fall down with the force of gravity. So what is keeping it from accelerating down? Well, that's going to be the tension force of that string. So tension is always on the string pulling away from the object. Normal force, so this is the confusing one on this side. Normal force is a force on a surface, by a surface, on an object. So we could look at this cup right here again. The cup has gravity pulling down on it, straight down. But why isn't the cup accelerating down? We know that F equals ma, right? So if we have a force and the sum of the forces on that object are not zero, then there should be some acceleration. So since this cup isn't accelerating, we know that there has to be another force in this up direction. So this is my evidence for this normal force, which we're just going to call Fn. So basically, every kind of surface exerts this normal force. The reason why it's called normal force is because it's always perpendicular to the surface. So if we had an object on a slant, say we have an object on a ramp, we put our cup there instead, not a nice place to put your coffee, then the normal force would be in this direction. So we're not really going to get into this until about next week. So normal force is always perpendicular to the surface. Then we have these long-range forces. These different kinds of long-range forces are all fundamental forces. So basically, you and I, when we throw a ball or something like that. So here I am. I'm going to try to throw a baseball over to my friend over here. So if I want to throw this ball this direction, the only forces I can exert on this ball in order to get it moving are going to be contact forces. Me pushing on the ball, so the pitcher does his wind up. During that whole path, he moves his arm around, and then he releases the ball. As soon as he releases the ball's traveling at a constant speed. Because we cannot exert long-range forces. The only kinds of forces we can exert are contact forces. These long-range forces, gravity obviously being one of them, we're always going to be pulled down towards the center of the Earth, unless we get very, very far away. So this is always going to play a role. Then we have electric and magnetic forces. These we're not really going to see until next semester. Here we have our everyman cue ball playing tug of war against black hat. So we need to draw a free body diagram of these two guys. So let's just look at cue ball over here. Has a mass ma. What are the forces on cue ball? First of all, let's just say that our acceleration is 0. So these two guys are at a standstill. It's a brutal contest until the end of times. So what are the forces on cue ball? Well, the tension in this tug of war is obviously going to play a role. But since the acceleration is 0, then we know that that there must be some force in the other direction. And this other force is going to be frictional force. So we'll just do the F, comma, A. So here is cue ball's free body diagram, and now we're going to do a free body diagram for black hat, or red hat, as it were. So red hat has tension pulling this way, and his mass is mb, and something keeps him from going to the left, which also must be friction on his feet. Right, friction on B. So now, how can I compare these forces to each other? So let's write out Newton's law for cue ball. Here we have the sum of my forces. So I need to label which way is positive x. So I know which things to make positive and which things to make negative. So T is pointing to the right. Friction is pointing to the left. And then this all has to be equal to mass times acceleration. So since his acceleration is 0, that's going to be 0. So what I know is that T is going to be equal to FA, or this TA. I could call this TB just to be really uncertain about myself. Sorry, TA. Now we can look over here at black hat and do the same thing. So the sum of the forces on this guy is going to be minus TB plus F friction B is equal to MBA, which is 0 also. So here we're going to have FB is going to be equal to my tension B. So I have two equations and two unknowns, these two tensions, right? But one thing that you know is that the rope, right, pulling this way, we call that TA. And then TA is going this way. And then TB going this way. It is impossible for TA to be anything other than TB in magnitude, right? Because the rope would have to be exerting some force inside of itself. So whatever TA is moving to the right, TB has to be going this way, otherwise this rope is doing something very strange. So these two T's have to be equal to each other. So that means that FFB has to be equal to FFA. So here we didn't even look at what's happening with these different masses. But we can already work out, it doesn't matter what their masses are. If this acceleration is 0, it's pretty easy to see that these two frictions have to be equal to each other. Well, let's take a closer look at friction. Basically, what matters in friction. So what we found out is that friction is equal to mu times n. Now this mu is basically a material property. And it doesn't even depend just on which surface that we have. It depends on both surfaces together. So for instance, we can have a block of wood on concrete. And then we can have wood on wood. And these two will have different coefficient of friction. So it depends on the whole set of materials that you use in each of these cases. So all these kind of material properties are all kind of bundled up into this mu. And mu can be, in general, between 0 and 1 for most materials. So the other thing that we have for friction is that there's this n. And I really should be consistent and call this Fn, because this is our normal force. But I wanted to write out n because you may see it written this way in some cases. So mu times your normal force. So you may go, why doesn't the area matter, right? Why doesn't this matter? If you have, one object here, right? I can draw it out like this. So I have some big piece of concrete or something like this. And then now I'll put on one material here. And now I'll put on a much bigger block here. But let's say I push down with the same mg on each of these. Basically, both these two objects would experience the same frictional force if I tried to move it along the surface. It doesn't depend on how much area is in contact between these two surfaces. And the reason why is because if you zoom in on a surface really close, you might think that if you had glass on glass, maybe the surface would look like this. But the reality is that there's no smooth surface. Nothing can be infinitely smooth. What actually happens is that these surfaces have lots of defects. And even if they didn't have defects, even at a molecular level, there's all kinds of things that are going on. And what's going to happen here is when you have two surfaces, like for instance, maybe your book and the desk, you actually have very little amount of contact area between the two. Maybe only two tiny little pieces and some piece of area are actually in contact with each other. Much of the other surface is not touching the other surface. So this is not one of these absolute rules of physics like F equals ma, right? This is a law. This is always true. This is an empirical relationship, which is just a fancy word for it's good enough. Basically, this is what we found. We still don't really understand how friction works. There's a whole field called nanotriviology, which is looking at how surfaces talk to each other, basically. But this relationship is pretty much empirical, and this is kind of what we use for everyday practices. All right, so now let's look at two other kinds of forces that we're going to see in a lot of cases. One is F gravity, well, we've already talked about this from time to time. The force of gravity is going to be mg. Now what you need to watch out for is what is the sign of gravity. So in this case, you need to look at where is my plus y or x or whatever direction, and then gravity will always be pointing down. And in this case, you should really have a minus here if this is your FG. So the important thing with gravity is to look out for this minus sign and make sure that you're always drawing things out. So springs are a little bit more complicated. So F spring was found out to be minus K. I want to write out delta X because I think this will be a little bit more descriptive of what's going on. So let's take a spring and we can put a mass on it. And right now the mass isn't moving. We put it on some nice frictionless surface so that if there was any force on this mass, it would move. But right now we know that it's not moving. So we can just call this x equals 0. Now let's mess things up a little bit and pull the mass this way until it's sitting right here. So what we've done is we've displaced this mass by pulling at this delta x. So what you'll find out is that if we make a chart over here of the force of the spring on delta x, on delta x, is that if we pull it away, so delta x is positive, what we actually get is that Fs is actually pulling back. So this is pulling back. The spring pulls back towards the equilibrium point. And if then we push the mass this way, we end up with another straight line. So this relationship between the force of the spring and this displacement of the spring is called Hooke's law. Now Hooke was Newton's arch nemesis. These guys hated each other. And he worked out the relationship of ideal springs, and he wrote out this Hooke's law. So this minus sign is really important, and I'll just write it again just to show how important this is. But this minus sign is to tell you that this is restoring, basically. And this is a fancy word for it wants to go back to this equilibrium point. And again, this delta x is the displacement. Here we have an actress who's convinced to use a rope to save an informant. After she saves the informant, she begins to worry if the rope and its supporting structure is strong enough to hold both of them. Alright, so what I need to do is to draw out basically what's going on, and then I'll draw a free body diagram for everyone. So here is what's holding the rope. Let's just draw the simplest thing that we can imagine. So the rope is hanging down. So now we'll draw our actress, and she's holding onto the rope. And she is also saving our informant. So he's dangling on right here. Help me. Alright, so what are the forces that we have in this case? So let's consider our actress, MA, and then our informant, MI. So let's start with the informant. So our informant is hanging here, right? And so gravity wants to pull our informant down. So that's MIG. Let's just keep a common axis of reference here. So there's my plus x direction. I can call this x equals 0, it doesn't really matter. So MIG pulling down, and since they are not accelerating, they're just hanging here. I know that the acceleration of this guy is 0. There must be another force on this guy, and that's the force of our actress who's saving this guy. We can just call this T1. So T1 is pulling up on our informant. So now let's work out what's happening with our actress. So our actress is also hanging on, and there is some force of gravity. She has MAG. There's some tension in the rope here. Let's call that T2. And then there's also this guy is pulling down on her, right? There's not just her own weight. She's obviously being pulled down harder. So this is T1. Alright, so let's write down our equations for everyone. So sum of the forces on our actress are, look at what's going up, so that's T2. And then subtract everything that's going down. So T1 minus MAG is going to be equal to MA times A. In this case, it's just 0. So now let's write out what's going on with our informant. Our informant, T1, is going up. And then just his own mass is pulling him down. And this is equal to MI A. And in this case, I just wrote 1A because basically if anyone is accelerating, they both have to be accelerating together. So we'll talk more about this. So what we have is, this equation is pretty simple to solve. So here T1 equals MI equals T1 minus MIG equals 0. So that's really just T1 equals MIG, right? Great. So now let's look for T2. I can rearrange T2 is going to be equal to T1 plus MAG. So I can plug in what T1 is. So this is MIG plus MAG, which is equal to MI plus MAG. And I can work that in, and it's 1,227 newtons. So this result is really kind of intuitive. If the rope needs to be strong enough in order to hold her weight and his weight. And we knew that. Basically, we could replace both of them by one object that had the same mass, and this rope shouldn't know the difference, right? Oh, that wasn't enough for our director. The rope now is being fastened onto a helicopter, and he's going to pull the two away from a fiery inferno. Great. What is the max speed that they can undergo? And not the tension on the rope. So we know that that tension in the rope can't exceed this, or it's going to break, and we can't let that happen. All right. So in this case, we could write out the same free body diagram. So here we have our actress. I'm just going to do this real quick, and that's T2. We have MAG. Here we have our informant, and you can't distinguish the two. This is T1. There's also a T1 here. This is MIG. And we could write out what are the sum of the forces for the actress, what are the sum of the forces of the informant. But what we need to realize and stop here is that, what is the max speed? So in this case, right, my helicopter is here. Here's the blades of my helicopter. So now the rope is being suspended from this helicopter. The actress is hanging on, and the informant is barely hanging on down here. If they are all moving up at a constant speed, then what does that mean for the acceleration? Well, that means that the acceleration is 0. So in fact, this is the exact same problem that we saw before. They can be at a v equals 0. If the whole system isn't moving, then we know that the acceleration is 0. Or they can be moving at a constant velocity. In both of these cases, the acceleration is 0, and we only have to worry that the tension in the rope doesn't exceed this 1227 newtons, and that's less than our 1800, so our actress is fine. So one thing always to be mindful of in working out problems is, are you accelerating? Are you moving at a constant speed? This should be one of the first things that you include in these free body diagrams. Oh, and that wasn't even enough. Okay, so now the director said they must accelerate away, maybe because they won't escape from the explosion. All right, so now we have to draw things out a little bit more, and you're going to enjoy my sketch of this helicopter. Yeah. So this rope is hanging down. We have our actress and our informant. Okay, so now the whole system is moving up at some acceleration. And also need to be mindful of which way is my plus x direction. So I can just label the ground x equals 0. So now have I considered everything? Acceleration is up. So now I need to look at what are the forces on my actress. So sum of FA. So she has that tension pulling down. If you can't right away pull out this tension, then start off with the most easy object, which will be our informant. So our informant just has M1G, and then there must be some T1 pulling him up. And then I also know that his acceleration is up. So now I can write out some of the forces on my informant. And I'm going to have T1 minus M1G is going to be equal to MI times AI. And I can just go ahead and be a little bit redundant about this AI. We'll get back to that. So now for my actress now has T2, and that's what I really care about. It better not exceed this 1800. And then she has her mass, MAG, and she's also accelerating up. So have I included all the forces? This should be T1. Okay. So now what I do is I say everything up, so that's T2, and then minus everything down, minus T1 minus MAG is equal to, and then in this case, A is up. So that's the other thing to watch out for. If you had A going against this X, then this probably should be a minus. But in this case, plus X and A, they're both up. I'm good. So have I included everything? Yes. So this is the other thing we need to talk about. So here I had her acceleration, his acceleration. So I need to say, are these two accelerations the same? If they weren't the same, then one of these two would be pulling away from each other, and that would be no good. So these two accelerations we're going to say are the same. So let's go ahead and work out just rewriting this and solving for some stuff. So let's start with his stuff. So the informant has T1 is going to be equal to MIG plus MIA. All right. And then up here I have T2 is equal to T1 plus MA A plus MA G. So I can substitute this into here. So T2 is going to be equal to MIG plus MIA plus MAA plus MAG. So let's group all these accelerations together. So A, MI plus MA, and then group all the G's together. MI plus MA. Alright, so what I actually cared about was this acceleration. So let's solve for the acceleration. So I'm coming over here. So what I'm going to do is bring this term over to this side and then divide by this. So I'm going to get A is equal to T2 minus G M1 MI plus MA. And then now I have to divide by this MI plus MA. So what is this T2? I know that it shouldn't be any bigger than 1800. So the biggest A can be is when I plug in 1800. If I plug in anything smaller for T2, I'll get a smaller A. So I'm going to plug in 1800 in for T2, and I'm going to find out that A is equal to 4.6 meters per second squared. So this tells me that if the director wants this to work out, then he needs to make sure that this helicopter isn't going to accelerate any faster away from our fiery inferno, greater than 4.6 meters per second squared. Here we have a half a kilogram object, and I place it onto a spring. So let's go ahead and put that. And I should say that I put it onto a spring vertically. So here's my mass. And I watched the spring stretch 2 centimeters when I placed it on the spring. So from this, I can figure out actually what is the spring constant. So that spring constant is, when I look at Hooke's law, that's that minus kx. So the spring constant is this k. So let's do my free body diagram for this mass. So this mass has mg down. This is my plus x. And then there's the spring force up. And then my acceleration is 0. I let the system come to rest, and I just am watching that the spring is stretched this 2 centimeters. So when I sum up my forces, I'm going to get Fs minus mg, is equal to 0. So that means that my spring force has to be equal to mg. Great. So that spring force up is this kx. So here you can go, well, why did I drop this minus? I should just stick in a minus here. That minus is to let me know which direction this spring force is in. Here I've already told myself from this free body diagram which direction the spring force is in. So that's why you don't see a minus thrown in here. So we can work out what that spring constant is, and that's just mg over x. And I'll find that this is about 250 newtons per meter. Great. So how far, so now I'm looking for an x, does the spring stretch when I place a 4 kilogram object on it? So here I now stick a bigger object on. It's going to be 4 kilograms. And so I have mg down. I have my spring force up. and my acceleration still is 0. So here the sum of my forces on this object are going to be my Fs minus the mg is going to be 0. So that's not too different than I had before. So then now I'm solving for x, right? I wanted to know what this x was. So x is going to be equal to mg over k. In this case I have 4 times that 9.8 all over 250, and I'll work this out and get about 16 centimeters. So does this make sense? 16 centimeters? Well, this object was 8 times heavier than this, so it ends up stretching 8 times further. So this is our Hooke's law again. So if you remember that spring force, I'm going to draw it actually the other way because it may be a little bit more intuitive this way. So basically, the farther you stretch it, the more force you get, and the relationship is linear with each other. So 8 times heavier object is going to stretch 8 times further. Here we have our same spring, but now we get into an elevator. Whenever you see an elevator problem, that means you need to really be paying attention to these accelerations. Or is your acceleration 0? Is it up? Is it down? Make sure that you label where your plus x direction is. Make sure you label which direction this acceleration is. So now you're zooming off from the ground floor up to 127 floors, and you're accelerating at this 2 meters per second squared. Great. So we are hanging this mass. So how much is the spring stretched if we place this 0.5 kilogram mass on it? So what are my forces that I have? Let me just change this. So here I have mg down, I have my spring force up, and I've shown A. Great. So the sum of my forces is going to be Fs minus mg, and that has to be equal to ma. So now Fs is just kx minus mg equals ma. So then I know kx equals ma plus g. So then x, how much is the spring stretch? So I'm really looking for that guy, is equal to ma plus g all over k. And this is going to be equal to 0.5 kilograms, 2 plus 9.8, all over my 250. So x is going to be 4 centimeters. Now one thing to watch out for is the sign of this acceleration. So since we were going up, would you expect that the string should stretch? So we could work out what happens when a equals 0, and we know that that was that 2 centimeters, right, if a is 0. So does this result make sense? If we're accelerating upwards, should the spring stretch? So do you feel heavier in an elevator that's accelerating up? Okay, so the spring does stretch, so this makes sense with our reasoning. So watch out if you have an accelerating elevator. If it's going up, you might expect things to be heavier. If the elevator is accelerating down, then you can expect things to feel lighter.